Today we are moving on to a lesson 11.7 and we are in the home stretch. We have pretty much covered all of the formulas that you saw in your formula sheet with regard to surface area and volume. This last lesson we saw a little bit back, I believe it was in the area unit as well. And there's a direct relationship between the ratio of their sides to their surface areas to their volumes. In other words, if the ratio of their sides is A to B, the ratio of their perimeters is also A to B. Now, ratio of areas, if you think about area and surface area, that's two-dimensional. So when we move to two-dimensional, the ratio of their areas or surface areas is A squared over B squared. In other words, we just take whatever scale factor we got here and we square it to get to the ratio of their areas, which is the same thing as their surface areas. And finally, if you think about volume, volume is a third dimension, which means now we've added on instead A cubed over B cubed. And that's what the focus is going to be on. Let's go back and look at, though, first of all, in order to use this, we have to know that we have similar solids. So remember, to figure out if they're similar solids, we have to look at the ratio of their corresponding sides. So if you take a look here, we're comparing 8 to 12 because both of those are the height of that prism, and 8 over 12 reduces to 2 over 3. Then I'm looking at this base here compared to this length right there. That is already reduced. And then if you take a look at the last corresponding side, 4 to 6, and again it reduces to 2 over 3. So that means I know that these solids are similar because their ratios are the corresponding proportion, and the other pieces, they're the same shape as well. I just want to refresh your memory. Another way we could check to make sure these are the same is we could just go ahead and divide. In other words, I could take 8 divided by 12, and we end up with 0.6 repeating. I could go and take 2 divided by 3. Again, I get 0.6 repeating. And the last one, 4 divided by 6, and I get 0.6 repeating. So again, I know these solids are similar. So including that then, and including what we had at the top. So that means if I know the ratio of any one of their sides, and again we said it doesn't matter, is 2 to 3, that means the ratio of their surface area is 4 to 9. Because remember what we said, you take 2 over 3 and you square them. So you square the numerator and denominator. If I wanted to know the ratio of their volumes, I would cube it. Again, 2 to the third is 8, 3 to the third is 27. And I can quickly show you this one. If you think about the volumes of each of these, let's go ahead and look at the volume of this one. We'll just call it volume 1. It would be 2 times 4 times 8, which is 64. If we look at the volume of the second one, we've got 3 times 6 times 12, which gives us 216. So it should be, if I look at 64 over 216, and let's just reduce that, 64 divided by 216, I end up with 8 over 27, which is what I thought it should be based on that rule above. So let's look at the first two examples. All they want to know are these figures similar? So again, we have to check to make sure their corresponding measurements have the same ratio. I can see the radius here is 4, the radius here is 18, or excuse me, is 8. I can see the height is 9, the height over here is 18. And I can quickly see that both of those reduce to 1 over 2. So the answer is yes. Let's go look at the next one. I see 2 corresponds with 4, which reduces to 1/2. 3 corresponds with 5, that can't reduce to 1/2. So guess what? I'm actually already done. Notice these are not the same. And even if you add in that height, 6 over 10, that reduces to 3 over 5. But all 3 of these need to be the same in order for the solids to be similar. They are not all the same, so our answer is no in that particular case. All right, moving on to number 3, all they want us to do is look at what would the ratio of their surface areas be and the ratio of their volumes. Well, this goes back up to the top. The first thing I want to do is just go look at what is the ratio of their sides. Then I square it to get to the ratio of their areas, and I cube it to get to the ratio of their volumes. So the ratio of their sides in this particular one is 3 to 5. And so again, all I need to do is square that to get to the ratio of their surface area. So 3 squared is 9 and 5 squared is 25. To get to the ratio of their volumes, I go back to here, and again, I'm going to just draw an arrow. I want to raise it to the third power. That's a little caret. So 3 to the third is 27, and 5 to the third is 125. And again, I know we don't have the exact same calculator, but again, I can show it. You're looking for the little caret symbol right here, and that gives me 125. All right, let's go on to the next one. Again, they want us to do the same thing. First thing, and it doesn't matter which side I look at because I'm told the figures are similar. I'm going to look at the smaller ones, which is 10 over 4. And I'm going to go ahead and reduce that to 5 over 2. So again, to get to the ratio of their areas, we want to raise it to the second power. So 5 squared is 25, 2 squared is 4. To get to the ratio of their volume, we want to raise it to the third power. 5 to the third is 125, and 2 to the third is 8. Now we're going to see how can we actually use this to find surface area and volumes without having to go back and reuse our formulas. Okay, again, they tell us the solids are similar. We have to find the surface area of the shaded figure, which in this particular case is the cube on the right. Now, as I said, because they're similar, we don't have to go back and reuse that formula. So let's look at their steps. Find the ratio or the scale factor of the dimensions. It is 6 over 8, and again, let's go ahead and reduce that to 3 over 4. Next, it says think about what the ratio of their surface areas would be. Remember, to get from here to here, you want to raise it to the second power. So that means if I take 3 squared, I get 9, 4 squared, I get 16. It says set up a proportion with this ratio in the given surface area above. So I've got 9 over 16, and I've been told the surface area of this cube on the left is 198. I'm looking for this one. So here's where we're going to set up that proportion. We have 198 over x. And you might be asking, well, why do I put the 198 on the top and not the bottom? Because remember, this 198 corresponded with the side length of 6, which was 3, which was ultimately 9. Now we're going to cross multiply, and we can solve. 9x equals 16 times 198. And we're going to divide by 9. Okay, let's go on to the next one. And similar to what we did before, only in this case we're talking volume. So first thing, we have to find the scale factor. One of the sides is 8, this one is 3. If I'm going to volume, remember that's third dimension, so that means I need to raise each one of these to the third power. So I'm raising 8 to the third and 3 to the third. Well, 3 to the third I know is 27, 8 to the third is 512. So that means the ratio of their volumes would be 512 to 27. I've got 512 over 27, and I've been given the volume of the smaller pyramid is 54. Well, that would go with the 27 down here because that went along with the 3. So I've got x over 54. Again, we're going to cross multiply 27x and then finally we'll go ahead and divide by 27 and we end up with the volume of 1024. Okay, I'm going to add one more just to kind of increase the difficulty level a little bit. So again, we're going to say that we have similar solids with surface area of 18 over 32 and the larger volume is 192, and we have to find the smaller. So I tried to increase the difficulty level a little bit. So in this case, I don't have this ratio of their size, but I do have the ratio of their surface areas. So what I kind of try and set up, this is like the 1 dimension, this is 2 dimension, this is 3 dimension. Or in other words, this is volume, this is area, and this is side length. So in this particular case, I've been given the ratio of their sides is 18 to 32. Let's go ahead and reduce that. That's 9 to 16. Now remember, when we were here to get to here, we raised it to the 3rd power. Let me say it again. Normally I started here and I raised it to the 2nd power, the 3rd power, depending on what I was looking for, but here I'm going to go backwards. So the opposite or inverse operation of squaring something would be square rooting. In other words, I want to square root 9 and I want to square root 16. That will give me the ratio of their sides. And let me give you a second just to look at that again. And again, you can check it. 3 squared gives you that 9, 4 squared gives you that 16. And now to go from here to here, we have to raise each one of those to the 3rd power. So we get 27 over 64. Now we're ready to set up that proportion and solve. Remember, I had the larger volume is 192. So that's going to go with this larger number here, and I'm looking for that smaller volume. So again, we're going to go ahead and cross multiply. 64x equals 27 times 192, and then we'll divide by that 64. And we end up with the volume of 81. So as I said, the whole point is we're noticing we don't have to go back and use all of those formulas again. We can simply use the fact that we know the relationship between the ratio of their sides, the ratio of their surface area, and the ratio of their volume, and simply set up a proportion. I encourage you to get this done. I will be on Zoom as I normally am. Let's see, at 1:30 on Wednesday, and then 8:30 and 11:30 on Thursday. So I encourage you to get on, and I can help work you through the Math Excel if you need it as well. Thanks so much. Have a good day.